Okay, so last day, last lecture. I guess people are also getting tired. No. So the last one I will briefly discuss is open-closed B model. Again, open-closed can mean a lot of things, and I guess you can do this one geometrically or do this one categorically. And we're going to focus on geometry. So far, what we have been discussing is the following. Like, at this moment, we describe like the B model closed string field. I explained how this is related to a generalized version of B field theory. And that I developed with Kevin Costello, and what is the classical geometry and how to quantize it. Now, this is basically for closed string, and today we're gonna move to discuss a little bit about the open string story, and basically this starts with Witten. Yeah, it's hard to imagine like this is a 33 years ago. Is it? True. The counting is correct, yeah. 33 years ago, yeah. Okay, anyway. I mentioned in the first talk, but let me just quickly remind you, like, there are two versions of open string field. Like A model, open string, field theory, as described by Witten. It is a version of like a Chern-Simons theory plus incidental correction. And B model open string field equals holomorphic Chern-Simons theory. Okay. That's the kind of object we will discuss today. In your group, everybody is familiar with this holomorphic Chern-Simons? Donaldson Thomas and... Okay, so anyway, let's start with something basic, and I will tell you like how to incorporate this data into what we have discussed so far. So, for simplicity, let's work on Calabi-Yau threefold. And suppose I have, let's say, a holomorphic vector bundle on X. Then the data of this holomorphic Chern-Simons associated to this pair is the following, like the fields. I apologize, I'm going to use the same notion, but there are too many E's, so I can use this E for today. This is the fields for this holomorphic Chern-Simons theory. Like anti-double complex valued in this endomorphism bundle and should degree by 1. I'm going to call an element here A. So this is like a gauge fixed, BIST gauge fixed fields. Like the original field is given by 0, 1 form. So after degree shift by 1, that's the physical degree, 0 element. So it's given by, physical field is given by a 0, 1 form valued in this endomorphism bundle. And the action functional, it looks very similar to Chern-Simons, but in the complex setting, so something like that. So by this combination, you basically create some kind of zero something form, and then you wedge with omega volume form to get a like 3-3 form, and you top form, and you integrate along x. And that's the holomorphic analog of Chern-Simons theory. So this is a holomorphic.
Trace.
Oh yes, a trace map. Yes, thank you. Trace, because it's like matrix value after trace. And this is holomorphic Chern-Simons in the so-called in the BV formalism. And I just mentioned, but let me just explain again the meanings of this data. Like so, whenever you have an element here, you see you have like on Calabi-Yau threefold. You have 0 form, 1 form, 2 form, 3 form, and they decompose into like such a way. And this 1 form part is really the physical gauge field. Describe the 0-1 connection. This one is about a symmetry, and this is called a gauge field. Gauge. This gauge is about the gauge symmetry. Yeah, that's the field of the gauge theory. Yeah. But that's called a gauge field in physics. Yeah, like connection form. Yeah. It's not a field for the gauge symmetry. Ghost is a field for the gauge symmetry. Yeah. Yeah, you're very precise. But this is what physics use. Okay, and let me call this one physical field. Probably you will feel better. Physical field for the gauge theory. And this is like anti-physical field. And you see clearly there's a pairing between one form, 2 form here. Same pairing. And there's the anti-ghost. That's why you have the physical field, which has a particular gauge symmetry generated by this ghost. And then in the BV stuff, basically the -1 shifted story, you add into the other copy, and that's what's happening.
The degree of that one.
Yeah, the degree, because of the degree shifting, so this now becomes 0. Yeah, and just 1, 2. Okay, so the equation motion basically. Okay, let's say for the physical field. One form, it basically is a del bar A1 plus 1/2 commutator. And then this basically describes a new holomorphic structure on the bundle. It's like a let this connection, let's call this one connection 0-1 connection by del bar plus A1. And this equation says like this one squares 0. So defines a new holomorphic bundle structure on E. Well, that's why people say like this holomorphic Chern-Simons describe the critical locus of this holomorphic Chern-Simons describe the moduli space of vector bundles, holomorphic vector bundles. Okay, that's the basic data. So as a comparison, like for the closed string data, the equation motion describes the deformation of complex structure, or if you want to add a little bit more together with the holomorphic volume form, the open string data describe the deformation of like holomorphic vector bundle. Okay, and then this whole thing like is -1 shifted. symplectic. With the pairing, let's say, if you pair two forms, like alpha and beta, you basically integrate along this manifold. And that's the pairing. So again, you want to do quantization. So you will basically look at the inverse of this pairing and do some renormalization. So the shifted Poisson kernel. Again, it's by the inverse of this symplectic pairing. And this is literally just integration. So the inverse is given by the delta function. So it's the distributional value of the product. Okay, that's the same data as we discussed before. Now, this Poisson kernel again describes a classical B-wave bracket, and this is not this. It's different from the closed-string case. The closed-string case, the Poisson kernel is highly degenerate. In the open-string case, this pairing is basically non-degenerate pairing, so which works better in a way. So, but this one defines, for example, a B-wave bracket for local functional in the same way as before. Let's say I1, I2. I'm going to use this open string bracket for this bracket here to distinguish with the closed string bracket. I'm going to use a C for closed string later because we're going to write down the corresponding equation for open closed. So this bracket between local functionals at this moment is well defined. Just because for I1 and I2, they are both given by some integration, and the same issue, like if you insert a delta function, the delta function kills one of the integration, you end up with some integration, and this is still a local functional. And at that same issue, we have like, okay, we have this data, and then we can show this action functional satisfy the classical mass equation. So basically, if you look at the bracket of holomorphic Simons with itself, this one equals 0. This is the classical mass equation for holomorphic Simons. And another way of writing this is like the physical way of writing this is the following. If you write like the variation to be the bracket with the holomorphic Simons, the B-wave bracket, the so-called BIST transformation. For example, if the way you calculate this one, arising from this action functional, you see like when you take the bracket, you kill one of the a's, the delta function kill one of the integration, then this variation basically, if you do the variation for a, you get the del bar a plus this data. And again, this zero locus of this variation is the equation motion as expected. And this classical mass equation basically says like this, the square is 0, also expected. And another way to encode the same data is to say like this differential basically describes the Chevalier-Ellenbach differential for the differential graded Lie algebra. That is the same thing as saying that this object without shifting is a differential graded Lie algebra. And this is essentially the same data. And then the corresponding BIST differential is the Chevalier-Allenbach differential applied to this differential graded Lie algebra. Okay, so far the story is the same thing as before. Now, we need to discuss somehow the data in a bigger space, and we want to encode all these bundles into something simpler. So one way to do this one is to work with the matrix of very large rank.
So what's the DGLA in this case? Which one do you use?
The D bar in bracket.
But then you are not using P for foundation.
No, this works in general. This actually, yeah. But I write this, but this is in general, yeah. So somehow a bit more universal. We can embed this data into something lies in a very big matrix. So, for example, maybe just say a few words. So, for example, you can choose some very ample line bundle to some EG. We can embed this bundle into there are some very ample line bundles, something like that, for M very big.
You better some bundle or just a combination?
No, it's really as a holomorphic vector bundle.
May not be able to do so.
Which one? It's a really sub-bundle, holomorphic. Yeah.
If you can do that.
Yeah. But if you on a projected manifold, you can always do that. You can basically twist, tensor this. You find the global section of this one, generate.
Zero.
Yeah, I have to tensor this one very ample line bundles. So that's why I need to embed this one into something very ample. Yeah. So basically, you tensor this one. This is the same thing as finding, for example, the dual. It's basically finding some global sections. You tensor this one, some very ample stuff, and very ample one. So such that this is generated by global sections, then leads to this map. So it works on projective manifold. Yeah. But just some basic. Just to illustrate the basic idea, but you can always do this one on projective manifold. This is like very ample, very ample enough. So in this way, you can split this embedding by. It's a complex splitting, not holomorphic, but you can always split in a way by choosing, for example, some permission metric and blah blah. So you can represent basically this is the same idea used in this algebraic K-theory and things like that. So this E can be represented by some kind of matrix, idempotent matrix. By some matrix, idempotent matrix. Let's say because endomorphism of this guy is literally given by a matrix. So let's say P is the element of M by M matrix valued in smooth functions, compact valued smooth function on X, such that the P square equals P, and this bundle is given by the projection by this matrix of this bundle. So this is smooth splitting, not holomorphic splitting. You always can do something like that. And then you can also study the properties of this projection as a part of data encoding this bundle. And then you can encode this, for example, using this projection left and right, you can encode these endomorphisms by embedded into represented by something that a very big matrix. It has to be very big, big enough. And then eventually, to incorporate all the data of this bundle, we need to make the n to be very, very big. But anyway, so I will try to tell you what's happening when you take n goes to infinity. So basically you can work with large matrix and try to remember to, whenever you want to come to discuss some particular bundle, you work with particular idempotent element and to insert into this theory. So instead, we're gonna, at the universal level, we're gonna work with very large matrix. So that's the we focus on. For example, let's call this one En, the book complex, valued in this m by m matrix, and whole thing shift by 1. And I want n to, because this one, at different ends, there's a compatible embedding. For example, this is embedded into m+1, etc. And then we want to work with something that is compatible with all this kind of direct system. So we look for some kind of functional on E for each n, which is somehow stable under this embedding. Somehow it's stable in the sense like the way it looks like it's stable. So let me say which has a stable expression when n goes to infinity. So there's a name for this one. I mean, I'm gonna be a little bit awake. So there's a precise definition for this one. We call this one admissible functional. But let me just tell you one example to illustrate the idea. So, for example, this guy is admissible trace. This is one of the terms lies in this transitions, this qubit interaction and integrate. This one is admissible because the same expression works for all fields and it's compatible with this embedding, so the same expression. This expression itself doesn't depend on n, although the field itself, the field here you can say it's lies in here or lies in there, blah blah blah, but the expression itself doesn't. Okay, that's one of the things we're going to work with. So the general idea is something very similar. You don't want something which depends on the rank when you write down the action functional. Okay, now let's study this Largen limit. And let's look at this kind of Largen duality.
But you need a functional to be related to more kinds of holomorphic functions.
Yes, so this one is related, but there.
But you need the bar to be zero.
No, because okay. So if you look at the variation for the holomorphic transitions for this particular theory, because you do the variation for the whole space of fields, then you get like on trivial bundle. But somehow, if you work with a particular theory, you want to do the variation along in the category of in the space of this particular representative in that class. You do variation inside this class. You got the holomorphic bundle represented by this bundle. So it depends on how large you want to do the variation. But it's a big data. Like you can write down some action functionals, and if you
Which action function will describe the Largen space?
so the action functional is still work with like holomorphic Chern-Simons, for example. So here your starting point. So we start with holomorphic Chern-Simons. the same expression. But if you want to do the variation of the Holomorphic-Simons for all fields here, you just get this trivial bundle, right? Yeah. But you want to obtain other bundles. So you can only have to work with the sublocus of this field.
So you need to have p-squared.
Exactly, you have to work with this data. That's right, yeah. So you have to do variation in that small locus.
Restrict to the.
Yeah, exactly.
Right.
Yes, so you have to restrict this one to a subset and do variation there. But this is some sort of more universal. Yeah. I think this is probably not extensively studied at some point, like how to work with like idempotent element with Holomorphic-Simons to do this, to encode the bigger moduli. I don't think this is probably no, but this is some idea you can pursue. But we have a particular reason for doing this, because there is an interesting Lagrange duality happening, like the following. So again, this is Chern-Simons theory. So let me explain the rough idea. So you see, like in this, now this Holomorphic-Simons theory, like that, and this is the action functional.
So we in this case, or we in the earlier case?
Now I'm going to work with this case, yeah. This case. Yeah, and now we want to let n goes to infinity at some point.
Are we assuming that p-squared will be?
No, it works with here. So
Here.
I'm working with all the possible way you can write down the action functional. Now you want to say, okay, once you have some kind of action functional, you want to restrict that one to some locus of this space to do variation. That's the second issue. Yeah. But I want to tell you, like, there's something happening at the universal level that all kinds of expression you can write down has an interesting phenomenon. Before you restrict to any kind of a subset locus. Yeah. So the point is the following, like in the ordinary Chern-Simons theory, like topological Chern-Simons theory, like in 3D, it's very rigid, and the only thing you can tune is the coupling constant, and the coupling constant somehow when OK, the level has to be integer. So that's the almost the only thing you can do for Chern-Simons theory. But for holomorphic Chern-Simons, there's a huge degrees of freedom you can deform. Unlike ordinary Chern-Simons, this one can be deformed, has a huge degree for freedom to deform. And somehow you see, like, for example, if you deform the Calabi-Yau structure, and you can deform this one accordingly, and that's one of the way you can think about it. And yeah, this is a question related to what we were discussing. It is the same question, basically. Yeah. And it turns out all the ways you can deform come from deforming this Calabi-Yau structure. That's the way, the version of so-called open-closed duality. But let me try to explain this one, like step by step. Okay, so to start, like let's for example, let's look at first order deformation. We can write down this deformation by holomorphic Chern-Simons goes to holomorphic Chern-Simons plus some local functional, local admissible. And because we want to preserve the classical mass equation, so we want this one to hold like the first classical mass equation at first order require, like, if you do this Biasi transformation for J, or equivalently, if you look at the B-wave bracket of J with the holomorphic Chern-Simons theory, this guy has to be 0. That's the condition for the first order deformation. Now you have to think about what this condition says. So this one says the following: like, remember, you can write down all possible local functionals, and this BRC transformation is basically the Chevalier-Allenbach cochain complex, the Chevalier-Allenbach differential. So this condition, the cohomology of this one, it really represents the Lie algebra cohomology. So basically, the J, the way you evaluate is a local dual or, for example, dually you calculate the Lie algebra homology of this all possible insertions. So you calculate the Lie algebra homology of this particular gauge theory. So that's the corresponding DGLA. So the double complex, like M matrix. And you basically calculate the Lie algebra homology. And the function of the dual is the way you evaluate these cycles.
So what's the Lie algebra?
Oh, sorry. Probably let me write. This is the double complex tensor with M matrix. So the DGLA is like differential is d bar. And the bracket comes from the bracket of the matrix here. And that corresponds to
So you're saying that J is the element there, or
J is the evaluation of this object, the dual.
J is a function.
Yeah. Dual of this object. So J is the way you evaluate these cycles. Or also this is Lie algebra homology. This is like really Lie algebra homology. And you can view J as Lie algebra cohomology if you want. And means like it's a given given by some integration. Yeah.
So it's not all of those.
Yeah, local, exactly. Yeah. And now this is usually very difficult to compute, but there's a remarkable theorem by Laudet, Quillen, Thigen. Which allows us to calculate the larger limit of Lie algebra homology. The theorem says the following: like, if you calculate this Lie algebra homology of M matrix valued in some ring or DG ring, and then you take the n goes to infinity limit. This is calculated by symmetric tensors of the cyclic homology by 1 of this ring.
So before the limit, does it have a map of one way or the other?
Yes, you can have a map, but it's with many relations. So it's like direct system. Yeah.
So this always
Yeah.
so the left hand
No.
always with the right.
That's right. Yeah, but these are relations. These relations get exactly. Yeah. So like this is like called cyclic homology. This one has a particular meaning. This is one way to represent this cyclic homology. Is like you put things on a circle. And there's a cyclic symmetry. this can be viewed as like cyclic invariant tensors. That looks very much like a boundary of the open string, right? I mean, that's a word sheet. That's exactly the case. So, in our case, if you apply this to this particular model, if you calculate the cyclic homology of this double complex, and this is like a debug resolution, and then you will find basically this Hausdorff-Kosten-Rosenbach theorem tells like the way you calculate the cyclic homology is like a de Rham differential, similar to the Rham complex, with a little bit shifted by this Kunis operator, and the Kunis operator is here is the Rham differential, so it's basically calculated by this complex. Negative orders, and when you
where's the T on the left-hand side?
there's no T here. The cyclic homology is calculated by this particular object.
Question. For this perspective, there's a T and a V.
T is really the way you represent cyclic tensor give you the T basically.
So you can't check the T for every F. You have to be calculated.
Yeah, you know, like when you got this bit, you know, this was basically the story is like the way the cyclic tensors of any kind of algebra is roughly speaking this the modeled. So you can replace the cyclic symmetry with different resolution, and then this cyclic stuff is calculated by this tensor, this model, like Hausdorff differential plus this T Kunis operator. So this object calculates the cyclic homology. It's a different model of resolving this cyclic symmetry. So, and if you apply this one to this case, this Hausdorff differential, Hausdorff homology of this like function ring is a de Rham differential, this de Rham differential forms, and this B operator is the de Rham differential, and this leads to this model. And here you see like this is a little bit sloppy. When you apply this one to, for example, the leading term, if you go beyond this order, it's 0. So it's really a quotient. So if you apply T del to forms with T to the 0, it's 0. This is what I mean by this complex. Or if you want, you can write this one as like quotient by relation, but this is the same object. Let me save some words. And
So what you think? So somehow J is something that is a function of this.
exactly.
So can you, without knowing the theorem, how does that?
I'll tell you how we write down formulas. Yeah, this writing down formula. I have to use the Poisson-Sigma model. Yeah. But let me first explain the kind of thing we expect, and then tell you how to write it down. So. Okay, so, but somehow this object, it's really, by the way, I want to write it down because this is a little bit sloppy. So literally, this really means.
This is not deserved by the operation.
Yeah, so that's why I want to write it down precisely. Yeah. So if you want to be more precise, this is really literally is given by. This is what I mean. Yeah. Yeah, that's more better. Yeah. Yeah. So, but I will still just write here, just save some chalks. So, but this is. Yeah, this is literally what I mean. Yeah. Okay. Okay, but somehow this guy is dual to local dual by a trace pairing to precisely, this is the negative part, and you have positive part. So this basically, you can identify this one with S minus, and this is basically S plus. And if you turn this one into differential form, the polyvector field, or if you switch this order a little bit, shift by degree. So basically, these two stuff are dual to each other. And just remember, like, this is related to S minus, this is related to S plus. And this one implies the following, implies the BCOE field equals, and the dual of this guy is the following, like, I mentioned, like, this is, you can view this one as a cyclic tensor I just mentioned, but I will write down the formula explicitly later. And then the way you write down the dual of the cyclic tensor is given by a trace. So physicists would say that this one give a deformation of the original model. This is by dual. It's a really given element here. I can write down the corresponding J. And this is a dual of this is cyclic tensor, means like this is like single trace operator. So single trace operator at n goes to infinity limit. This is a statement for, it's a famous statement in so-called ADS-SAT correspondence. So this one is the object you can calculate from gauge theory in the larger limit for the single trace operator. So you can design something here. And once you collect all this data, you observe this is the same data as the gravitational field. So this is, but this BCU field is a topological gravity. So the gravitational modes arise from the single trace operator at the larger limit. That's the statement for one statement for the ADS-SFT correspondence, the larger duality. Now, let me give you some examples, like how to realize this deformation by just this argument. So let me tell you some example. Oh, by the way, just let me know. This is so-called gauge gravity duality. And the stuff I mentioned here is basically a version of a gauge gravity duality in the topological B model. Now, let me give you some example. Suppose mu is an element of like poly K field. And by this observation, because this is dual to this object, in principle, I can write down a first order deformation of my holomorphic Chern-Simons specified by this choice of mu. So gives a first order deformation as follows. It's a rather explicit formula. Now my field is given by n by n matrix, and so by the following, let's call this one J mu equals trace mu contract A wedge dA wedge dA. So here you have k of them. That's the kind of deformation you can write down. This is the corresponding. By the way, the way you write this formula is arising from this dual is basically the way you describe like Hochschild, Kosten, Rosenberg, like the way you write down this polyvector field as a differential operator applied to something. So basically, this is the HKR theorem. Another way to express this HKR. Now it can be more complicated, like say, suppose if you add into descendant, let's say t to the m, it's getting more complicated. There's a precise combinatorial formula, but somehow you can find like J mu is some kind of linear combinations. Of some expressions of the type like trace mu can check with like say a wedge a to the L1 wedge dA wedge a to the L2 wedge dA etc. And a to the Lk wedge dA and with the Coulomb volume form with so this L1 plus L2 etc. equals like 2m. There's a precise formula for that. It's not easy to write down, but there's a combinatorial formula. And the way you write this formula is the following.
So mu will give you the information for each n.
Yes. And it's compatible, so it's admissible. The expression itself doesn't depend on n. That's what I mean by admissible. Yes. So it's really that deformation in the larger limit. And you can basically sometimes you can draw a picture like you have first order deformation. It's one bulk insertion and some boundary data from this connection, and then mu gives way to take the trace on the boundary. This is the first order deformation. This is what I wrote for this J mu. Now, there's a general formula for this. General formula for higher order deformation. At the classic higher order deformation of the classical Chen-Simons series, it means at the disk level. For higher order deformation at the disk level. And it's basically by calculating correlation functions in this so-called Poisson-Sigma model, but it's the holomorphic version. And also, you have to incorporate this T variable, which is about a cyclic structure. So there's actually a generalization of this argument by Weierwacher and Kalak. And there's a version of cyclic extension of the conceptual formality. Basically, you see, like you calculate correlation functions in Poisson-Sigma model, and you put the polyvector inside, and you can put this. You see, like a matrix in the larger limit. It's represented by a cyclic tensor. So basically, you can just write down some cyclic ordered object, and then you can calculate the corresponding correlation function. And originally, the work by Kontsevich, he did the case for a non-cyclic case. So you insert polyvector fields, and the boundary just write down some functions. But later, like Weierwacher and Kalak, they find a formula for extending this Kontsevich Poisson-Sigma model for cyclic object. So you basically encode this T's, and this has to be evaluated on this configuration space of endpoint in the interior and endpoint on the boundary. And so each cyclic object, like T's, will also basically lead to some kind of Chen characters arising from this circle bundle along this configuration in a rather explicit way. So whenever you see a T, you insert that particular two form representing the Chen character, and then just do the intersection, and they got this correlation. That is this gives rise to, for example, fourth order deformation of the holomorph chain Simons at a particular background of this mu.
So they need to compute the coefficient.
Yeah, they have just all these coefficients are given by this integration. Yeah.
They compute it.
Yeah. They have rather explicit formula for that. Yeah.
So all order, or is it always four?
No, all orders. So all expression. Yeah. So the new thing in this story is basically is the interpretation of T. So I have to replace. So the T is a degree 2 element, right? Whenever you insert T, you have to insert a 2 form associated with a circle. It's like a Lie bundle on it's like psi class, for example. So but you have to do it. You can do this one combinatorially. So every T represented is degree 2 is a 2 form. You integrate on the covariance space. That's the Chern character of the particular bundle. That's the new thing in this work. Yeah, cyclic formality. So using this cyclic formality, you can write down this correlation. On the full, like the deformation of this basically give you this holomorph chain Simons on this mu and A for any mu in this S plus. Just give you this formula.
Are you describing the first order, or
This is describe all orders, all orders in mu. This is really literally on the full space, not only the first order.
So you talk about the closed string on the master equation.
This is only for open string yet, so not the closed string. I haven't tell you the closed string.
So this is all orders you have the honest equation.
Yes, and then the y is yeah. I'm coming to this. Yeah, this is about the master equation. The content of the formality just says like this deformation is compatible with the closed string deformation. Yeah. Okay, so now let me just try to explain this open-closed mass equation. And now this is only for disk, and we're somehow interested in kind of deformation or some kind of distribution indexed by the following data. So we are interested in the following object. For example, I'm gonna write this one as like a genus G, and with H boundaries. So G is the genus. H is the number of boundaries. Basically, the number of like the cyclic tensors, if you want. So you can visualize this object as something that you want to calculate some kind of distribution or correlation functions where you have the bulk insertion in the interior and the boundary insertion for A on the boundary. And this is like cyclic tensors. The cyclic tensor means like in the larger limit. So this means like this example is like the genus 2 and the H equals 2, like 2 boundaries. And remember, like we have a bunch of cyclic tensors because I just erased this Lodé-Seeger and Quillen theorem. If you all this BRC cohomology is represented by tensors of the cyclic stuff. So basically, eventually, you write down the action functional in the larger limit. It's going to be functional on the mu and the tensors, like symmetric tensors of the cyclic tensors. So that represents basically some boundary data. Now, let me write down the corresponding mass equation. This is the work of T. Babak, but let me, I mentioned in the first lecture, but let me just write it down. So this object, genus G with H boundaries, whatever these are, somehow are required to satisfy.
If you have no A, then we didn't do because what we did earlier.
Yes, that's right, yeah. So no boundary, that's the pure closed string, yeah. So this one are required to satisfy, for example, this is like a Tillamook's open closed mass equation. This set of equations looks complicated, but let me just illustrate the basic idea how to view this equation, how to write it down. So roughly speaking, the equation looks like you look at all the possible degenerations of this Riemann surface of genus G with H boundaries. You look at then the BRC operator, this Q differential applied to whatever you wrote down, is represented by all the possible degenerations. That's the way you can write down equations. So let me just tell you how this works. So I give you some examples, like say, example, like at the disk level, like a genus 0 with only one boundary. So this is the kind of data we have. So we allow on the disk genus 0 and only one boundary. Then you look at all the possible degeneration, and the boundary of this configuration look like, for example, you can bubble the disk and you will find this object. This is the bubbling of the disk, and if you shrink, if you points inside can move together, and there's a bubbling of the sphere. So you can write something like let me write it in such a way. Let's see, this is a disk. And connect by something on the sphere. This is when some points in the interior they move together. And then how to write down the corresponding mass.
We need one more external link.
That's right. Some. If you want to be precise, yes. And the number of closure insertions, 1, 2, 3. I guess I need one more. Yeah. Okay. But it's distributed in different way, like 1, 3, and. Now, whenever you see this, you write down the equation, reads. So apply this Q to, for example, this action functional. This is my differential. Now use genus 0 with one boundary, plus this is the bracket. This is the B-way bracket in the open string selector. You have to insert this kernel. I just mentioned you have to insert this B-way kernel in the string selector, open string selector, write it down. But that's the. So this is in the open string selector, the B-way bracket, and here you have a bracket in the closed string selector. In the closed string selector. So this is like open string B-way bracket. In open string, this is in closed string. And that's how you write an equation. So
It's easy to see the coefficient.
it's,
Yeah.
this,
Because of the symmetry.
yeah.
And the psi is always constant.
Psi is very difficult. Yeah, science is very difficult. It's very there's some people write a bunch of papers just to explain the sign, but Yeah, this equation basically is conservative formality. So, which says like if you do apply this basically L infinity transformation on the closed string side and push to the open string, it becomes the open string infinity relation. So this is basically formality. Conservative formality. Conservative formality is about this equation, which says like the Pauli vector field. This is a map of Pauli vector field to like Hochschild cochance, which is the L infinity morphism. So this equation says like this is L infinity morphism. And this is the part where you see like this is a Holomorphic in this particular background. So when you solve mass equation, literally, if you solve Calabi-Yau equation, it's when at the critical point of this closed string sector, is when when the critical point is 0, then this term vanishes. You get a family of Holomorphic. So without this term, this looks like the mass equation for holomorphic Simons, right? So you get a family of holomorphic Simons. But it's only true if the equation motion is satisfied for Calabi-Yau. So you see, this requires what is I naught not? I naught is the one I wrote for I naught x. This is Bezier action for Calabi-Yau. So this bracket, it basically calculates the critical point of the classical B side. So the way the solution of the deformation problem is the zero locus of this one, when this is 0. So if you really solve the deformation problem, if you insert a good mu, which solves the Molecular line equation, is when this vanishes. So literally you get a holomorphic Simons, basically in the deformed background.
You don't have to, you only need the whole thing to be.
Yeah. This you can view this one as like a Cochan level or Chan level. You don't need to restrict to solution, but just to try to explain your question, like when you write down this family, you fibered over moduli space, then you got a Holomorphic Simons. But if you fibered over the chain complex, that's what you get. Yeah. Now let me say, I probably need.
There's a train to train now.
Yeah, that's right. I probably need 5 more minutes. Yeah. I think this is a very important point to explain. I wanna slow down a little bit. So now, second example. I want to just tell you like the question you asked. If we just in the case when there's no boundary, we should get back to the original quantum mass equation for the closed string, and that's indeed the case. For example, let's look at like genus 2 with no boundary case. So something will work with closed string, pure closed string. And then you see like the way you can degenerate. We know this modular space how they look like. You can have something like that. Oh, this is terrible. Okay, I think it's better. So you can shrink this circle; it becomes something like that, and you can have degeneration which split into 2 torus. It's a Nono curve, or you can bubble a sphere if you have enough Mach point. Something like that. Then you can write down the corresponding mass equation. This one says the following, like, so this Q applied to I2 naught. So this is purely genus 2 closed string data equals. So this is like it connects to itself. It's like a B-way operator contracting itself. It's like a BB operator closed string to genus 1. So this is just one loop connecting to itself. So this reads 1/2 genus 1 in the closed string sector bracket, and this is like sphere bracket of genus 0, genus 2. So this is precisely the genus 2 quantum mass equation. You see, like this is basically the h bar delta q plus h bar delta for I equals, like, say, I g 0 h bar g. And then you basically look at the specify this equation at the order h bar to the h bar squared term, so you read off this equation. So if you restrict just to the pure closed string, you just come back to the original model. So one more thing I want to explain is this guy. This is a new phenomenon, actually, we find in the B model. I don't know whether this is seen somehow in the A side or not. So, but anyway, this is when annulus. It's when this it's a genus 0, but with 2 boundary. And then you have a bunch of choices. For example, you can bubble the disk. Yeah, something like that. Yeah. And then you see, like, you can basically shrink this line. When you shrink this line, it becomes like a disk connecting to itself. You will shrink this line, it becomes 2 points glued. So what's really happening is this object glued. So it glue itself by glue these 2 points, the same thing as shrinking this guy. And then you can shrink something in the middle. Or you can bubble some sphere in the middle. And you can write down the corresponding mass equation. Say, for example, like Q applied to genus 0 with 2 boundaries has to be the sum of, this is like a Biasti operator, it's like computing the bracket with the disk amplitude. Now in the open string sector, this guy is interesting. This is like a one loop data from the open string sector. Actually, because it's applied BB operator, this is precisely representing the gauge anomaly, one loop gauge anomaly for the open string. This is applied BB operator, open string sector to this disk. Usually this is not 0. It's like if you work with like open string sectors, you will find like if you try to quantize Holomotion-Simons, that's going to be anomalous. Just like open string itself is not well defined at the quantum level, because you see, like when you open strings, the evolve must be connected to open closed string. So you need closed string to be the consistency of this quantum theory, and this is like an anomaly from purely open string side. And this is actually what's happening is the following: like, although open string itself is anomalous, but if you include closed string sector, and the anomaly will be cancelled out. So this is from this closed string sectors. So this equation, and plus the last one is like I not I two not. This closed strings equals to 0. So this term It's a one loop gauge anomaly.
I see.
I
Not the last one.
yes, this is here. Yes. One dot gauge anomaly. So this term is a one loop gauge anomaly, and this will be essentially cancelled out by this diagram. The other stuff like BRC transformations, so essentially killed by this diagram. This is a tree level amplitude in closed string. So this is famous so-called Green-Schwarz mechanism, which says like the one loop gauge anomaly will be cancelled out by tree level closed string factor if you look at the quantized theory. So this is a Green-Schwarz mechanism.
So you mean that if you quantize the open string, you move the closed string a little bit?
So basically, it says like the open string itself is anomalous. Yes, yes. And okay. Now let me tell you a theorem then before the end of this mini course.
So in the case when the space is points,
Again?
IGQ, right?
IGH, yes.
Right? When the x is at points.
Yes.
You know IGH.
Pure gravity? Yes, yes.
That's explicit.
Yeah. So now let me tell you a theorem. Yeah, the original theorem was stated on a flat space, but it's actually the same argument applies to local Calabi-Yau. But so let me just say this. So suppose let's look at the trivial one piece flat case and start with fix. Basically start with the first data is like admissible holomorphic chain assignments. Now what's funny is like if you try to solve this equation for the model I just explained, you really find there's an anomaly even for solving the couple system. And that anomaly comes from the fact that basically if you have after you do this kind of all this kind of diagrams, there will be some kind of a circle trace without any kind of insertions. And then we'll give you a trace of this object. A trace of this object without anything is like evaluated by n by n matrix. That's gonna be n. And this is gonna break everything down. However, you can somehow extend this a little bit by working with a super case. Like work with like a larger limit of the following model, like GL n/n model. You basically encode larger matrix, but it also encodes the odd direction. So this probably has the interpretation in terms of like a Brent anti-Brent system. This is something we need. And the action function is the same. And then you look at this first order deformation, that's gonna fix. Basically by HKR. Then, starting from this data, so once you have the super matrix, then this stuff is going to be zero on GL n/n. Trace 1 is going to be zero, and you don't have this anomaly. If it's not zero, then if you do this calculation, you will find some term, which basically this one of the anomaly will give you a term like a trace 1. This will be one of the anomaly.
Anomaly in the sense that you cannot solve the equation.
Yes, you cannot solve the equation. The way, basically, there's some terms here which is proportional to n, which is not BRC exact. Yes, this is only anomaly in this model. So that's why we want to kill this trace 1. And also, this also appears, for example, because we stay with the like admissible functions. This is a term which will break down the admissible as well, because it depends on n. I want something which doesn't depend on n as well. So it's also a different way of understanding this one. But anyway, so if you work with n/n, then this guy trace is going to be 0, and this normally disappeared. Then there exists a canonical quantization for all geners and H. So it can basically solve this equation for all kinds of Dirac open-closed mass equation. It can view this one as the quantum version of this cyclic formality. And actually, I mean, that's satisfying this kind of open-closed mass equation. And although this stated, the original paper is stated on this case, but actually you can show this argument glues on Calabi-Yau with a non-trivial sister action. So
if you add more n, but more further part, so then okay.
well, I need the trace 1 to be 0. So
They have to be both exactly.
yeah, that's right. So, and actually, just a remark, and you can show basically such quantization canonically glues to any local Calabi-Yau. So with a non-trivial sister action. And this is proved by at the level of using this deformation theory. But once we know actually all this open close. By the way, there's another way I want to mention. This is something we just know. And just another remark. This B theory coupled with Coulomb-Chern-Simons, this kind of open-closed B model. This theory, the bigger theory, actually is also UA finite. So it's possible to actually get more hands-on description, local description. In general, for any Calabi-Yau, yeah. Or any Calabi-Yau. I need a Kähler Calabi-Yau, yeah. So the theorem of Minhao Wang and Junrong Yan, they need the Kähler condition, compact or compact Calabi-Yau. It all works. Yeah. So this is UA finite. Yeah. That's work. Yeah. Not only this, the compactness is not issue. Non-compact works. D bar F works. Non-logismo twisted, it works as well. Yeah. So it means like all this quantum equation. So I write down some kind of complicated equation, but if you really want to write it down, you have to renormalize everything at a particular scale to write down this equation and solve it. But by this property, it's likely to write down a more local version of this equation on any Calabi-Yau. So just so far we just don't know what is that. This is a question I asked yesterday, like, yeah, for students here if you want to do a PhD. This is if express the renormalized local expression of this guy. Just to apply this theorem to Coulomb-Chern-Simons and see what kind of local renormalized mass equation look like. So you will basically, if you calculate, you will observe some higher bracket term appearing in this model. So it's like originally you have d bar and you have a bracket of local functionals, and then you probably will deform this bracket a little bit, and probably will have a higher bracket, which encodes the quantum mass equation for holomorphic Samus. And you know it's going to be anomalous, and then using this one, you can figure out the meaning of this anomaly as well. So, but that's going to be left for future.
But when you say GLNN, I mean, it look like, can you just look at like in K-field, you look at two vector bundle of very high rank, but you look at the difference with the rank 0. That's all we do in K-field. You minus you zero.
Yeah, the issue is like what kind of bundle you want to work. Yeah.
So forget the
Yeah. So this is really at the level of like all the evaluations, so functionals. So this construction for all the possible functionals. But if you want to apply this to particular type of bundles or chain complex bundles, a particular object, you basically, so you see like another way to see this data is like you have to want to work with chain complexes, and you want to encode all this chain complex into a big super matrix, and then you have to work with like a particular idempotent object, or
so this is really you're looking at like a virtual bundle of rank 0.
That's right. But if you want to resolve it, you write it down explicitly. You want to write down a particular idempotent and representing the bundle, and you work with that particular locus. But that's not known, at least to me. So I hope, yeah, this is probably the end of this mini course. So thank you very much.